In this lecture, we will discuss properties of recursively enumerable and recursive languages. A language L is called recursively enumerable if the language is accepted by a deterministic Turing machine. The name recursively enumerable comes from the fact that there is also an equivalent another definition, namely we can define that a language L is recursively enumerable if there exists a Turing machine that enumerates all the words in the language L. And you can think of this as follows. The Turing machine enumerates the words in the language by writing all the words on the tape after another. So it writes W1, W2, W3, W4 and so on, separated by some special symbol, in such a way that the language L is the set of all the words that appear between these special symbols. Now, if we have a Turing machine that writes all these words behind each other on the tape, then we call this sequence W1, W2, W3 a recursive enumeration of the language L. If this language L is infinite, then clearly the computation will take forever. We have to write infinitely many words on the tape, so the computation will never stop. These two definitions of recursively enumerable languages are equivalent. Assume that we have a Turing machine that enumerates all the words of the language. And now we want to make from it a Turing machine that accepts input words that are in the language. How do we do this? We make a machine that takes an input word, then it runs the Turing machine that enumerates all the words in the language, and as soon as the input word appears in the enumeration, the Turing machine accepts the input word. And if the input word does not appear, it will simply wait forever. It will never appear. It doesn't accept, it computes forever, so the word is not accepted by the Turing machine. Now reversely, if we have a Turing machine that accepts the words in the language L, and we want to make from it a Turing machine that enumerates all the words in the language, we can do this as follows. We take our machine that can accept the word in the language L, let's call it M, and now we make from it a machine N that enumerates the words in the language. First of all, our machine N can, of course, enumerate all the words over the input alphabet sigma. So it's simple to enumerate all the words over the input alphabet. Now, additionally, our machine can also run the acceptor machine M in parallel on all these words. So it will run our machine M on all the words over sigma in parallel, and as soon as it finds that one of these words is accepted, it puts it in the enumeration. And eventually, every word in the language will be accepted, so every word in the language will eventually appear in the enumeration. So if a language L is accepted by a deterministic Turing machine, then we have such a recursive enumeration of all the words in the language. We have a Turing machine that computes the sequence of these words. The set of all Turing machines is recursively enumerable. Formally, we mean here that the set of words describing Turing machines is recursively enumerable. We've already discussed that every Turing machine can be described by a word. So why is this set recursively enumerable? If we have a word describing a Turing machine, we can simply run a parser that checks whether this word is a valid description of some Turing machine, and if so, we accept. So it's very simple to make a deterministic Turing machine that accepts the set of all words describing Turing machines. So this also means that we have a recursive enumeration of all Turing machines. So we can make a Turing machine that one by one enumerates every single Turing machine that exists. And this recursive enumeration, formally again, it's an enumeration of all the words describing Turing machines. This enumeration we can then give to a universal Turing machine which can execute all these descriptions. So we can actually make a Turing machine that enumerates every Turing machine that exists, and we can use also a universal machine to at the same time run or simulate each of these machines. Now let's have a look at the properties of recursively enumerable languages. If L1 and L2 are recursively enumerable languages, then the union of L1 and L2, as well as the intersection of L1 and L2, are again recursively enumerable. So the class of recursively enumerable languages is closed under union and intersection. Let's prove that. Since L1 and L2 are recursively enumerable, we have deterministic Turing machines M1 and M2 that accept L1 and L2. Now we want to create a Turing machine M that accepts the union or the intersection of these two languages. The main idea is that our machine M runs M1 and M2 in parallel. So it will run both M1 and M2 at the same time. Of course, we don't have real parallelism, but we can create a machine M that alternating simulates one step of M1, then one step of M2, one step of M1, one step of M2. We run both of these machines. We have to make sure that they don't influence each other, but this can be achieved by using a larger alphabet. For example, we can use an alphabet of pairs, where M1 only operates on the left entry of the pair and M2 on the right entry of the pair. And we now run them alternatingly one step M1, one step M2, and our machine M accepts the input word if one of them, so either M1 or M2 accepts. So as soon as M1 accepts or M2 accepts, then our machine M accepts. If we do this, we get that M accepts the union of the two languages, because M runs these machines M1 and M2 in parallel. When is a word in the union of the languages? If it is at least in one of the languages, that means that at least one of these accepts. And if one of these accepts, M accepts. Now for the intersection, we need a different acceptance condition. If we want to have the intersection, then M will wait until both M1 and M2 have accepted. So if we wait until both accept, then we get the intersection of the two languages. So we can construct a machine for the union as well as a machine for the intersection by running both machines in parallel, simulating them, alternating one step the first machine, one step the second machine. What about the difference? Does the same idea work for L1 minus L2? It does not work. The problem here is that if we say we want the set of all words that are in L1 but not in L2, we have a negative condition. We want to know that the word is not in L2. And how should we figure that out? A word can be not in L2 if either the machine M2 reaches a non-accepting halting state, or if the machine M2 computes forever. But we cannot know whether it will compute forever, so we can never be sure that the machine M2 does not accept a certain word. So this language cannot be accepted using this construction. And we will actually see that this is really not possible, that there are cases where this language L1 minus L2 is not recursively enumerable. The class of recursively enumerable languages is not closed under complementation. So there are recursively enumerable languages L for which the complement of L is not recursively enumerable. So let's prove this. We have already discussed that the set of all Turing machines is recursively enumerable. So we have a recursive enumeration of all Turing machines. So let's say that our enumeration is M1, M2, M3, and so on. So we have a Turing machine that outputs M1, M2, M3, and so on after one another. Now we define a language L as follows. We say that the language L consists of all words a to the power I, for which a to the power I is in the language of the machine Mi. So the ith machine in this enumeration. Now this language L is again recursively enumerable. So we can make a deterministic Turing machine that accepts the language L. How do we make this? We make a Turing machine that takes a word over the alphabet that contains just the letter A as an input. So it takes a word of the form a to the power I as an input. Now this machine runs the machine that computes this enumeration. So it enumerates the Turing machines M1, M2, M3, and so on. And we stop as soon as we have enumerated the machine Mi. So if our input word is a to the power I, then we construct the machine Mi. Now we have the machine Mi, and now we can run a universal Turing machine that simulates Mi and that checks whether a to the power I is accepted by Mi. And if it is accepted, then our Turing machine accepts the input. So we have constructed a deterministic Turing machine that accepts an input a to the power I if and only if the machine Mi accepts the input. We have used that we have a Turing machine that enumerates all Turing machines and that we have a universal Turing machine. We've combined both of them to construct the Turing machine for the language L. So our language L is recursively enumerable, but what about the complement? Let's assume that the complement was also recursively enumerable. Then the complement must be the language of one of our Turing machines in this enumeration. Because if the complement is recursively enumerable, it is accepted by a deterministic Turing machine. We have an enumeration of all deterministic Turing machines. So this deterministic Turing machine must appear somewhere in this enumeration. Let's say it's the machine Mk. So the complement of L is the language of the machine Mk for some k. Now what do we know? We know that the word a to the k is in the complement of L if and only if a to the k is in the language of Mk, simply by this equality. Both languages are the same. So a to the k is in both languages at the same time. Now a to the k is in the language of Mk if and only if a to the k is in L by definition of L. So we have that this is equivalent to a to the k being in L. But now we have derived a contradiction, because we have that a to the k is in the complement of L if and only if a to the k is in L. A word cannot be in the language and the complement at the same time. So our assumption was wrong. The complement of L cannot be recursively enumerable. So we have shown that there are recursively enumerable languages for which the complement is not recursively enumerable. And as a consequence, it also follows that the difference of two recursively enumerable languages is not always recursively enumerable. Because we can define the complement of a language as the set of all words over an alphabet. This language clearly is recursively enumerable. We just make a Turing machine that accepts all input words. Minus the language L. So if the difference would preserve recursive enumerable languages, then also the complement would. But we have shown the complement does not always preserve recursive enumerability. So the difference also does not preserve recursive enumerable languages. The class of recursively enumerable languages is closed under concatenation. So if L1 and L2 are recursively enumerable languages, then the concatenation of L1 with L2 is recursively enumerable again. If L1 and L2 are recursively enumerable, we have Turing machines M1 and M2 that accept L1 and L2 respectively. Now we construct a Turing machine that accepts the concatenation of the two languages. How do we do this? First, we need some auxiliary definition. We say that a split of a word W is a pair W1, W2, such that the word W is the concatenation of W1 and W2. So W1, W2 is a split of the word W. And we say that such a split is good if the first part of the split W1 is accepted by M1 and the second part of the split W2 is accepted by M2. So it's a good split if the first Turing machine accepts the first part, the second Turing machine accepts the second part. Now, how do we make a machine that accepts all words in the concatenation? We make a Turing machine N that takes an input word W and first it computes all possible splits of the word W. There's only finitely many splits of a finite input word, so we can compute all possible splits. Next, our Turing machine checks in parallel whether one of these splits is good. So it will run the machines M1 and M2 several times in parallel for each of the splits in parallel. And again, we don't have real parallelism, but we can alternatingly run one step of one machine, then one step of the next machine, one step of the next machine, and so on. So we run them alternatingly, such that all of them progress. And as soon as we have found that one of the splits is good, so as soon as we found one of the splits where both machines accept, so M1 accepts the first part of the split and M2 accepts the second part of the split, then we accept the input word. And it follows that the language of our machine that we have constructed is the concatenation of L1 and L2. The class of recursively enumerable languages is closed under the Kleene star operation. So if L is a recursively enumerable language, then also L star is. Let's prove this. Since L is recursively enumerable, there exists a Turing machine M that accepts the language L. Now the idea of the construction is similar to the concatenation of languages, but now we split the input word not just in two parts, but in n parts possibly. So let's call this a partitioning. We say that a partitioning of a non-empty word W is a sequence of non-empty words W1 up to Wn, where n is at most the length of the word W, such that W is the concatenation of W1, W2 up to Wn. And we call such a partitioning good if the Turing machine M accepts each of the parts. So if it accepts W1, W2 up to Wn. Now we construct the Turing machine N that accepts L to the star as follows. This Turing machine takes as input a word W. Now if the input word is empty, then it's very simple. Then we don't need to split. Then we simply run the Turing machine M and we see whether M accepts the empty word. So let's assume that the input is a non-empty word. Then our machine N computes all partitionings of the input word W. After having computed all partitionings, we run the following check in parallel. For all partitions, we check whether they are good. And we run this check for all partitions in parallel. As soon as we have found one partition that is good, so one partition where the machine M accepts each of the parts, then we accept the input word. And as a consequence, the language of our machine N is L to the star. Because a word should be accepted, the word is in L star, if we can partition the word in parts such that each of the parts is in L. We can construct the word from building blocks in L. And that's exactly what we check here. We first compute all the possible partitionings into parts, and then we check whether one of these partitionings is good, in a sense that all of the parts are from the language L. The recursive languages are a subclass of the recursively enumerable languages. A language L is called recursive if L is recursively enumerable and the complement of L is also recursively enumerable. So we know already that not every recursively enumerable language is recursive. A few slides back we've seen that the class of recursively enumerable languages is not closed under complement. So we have recursively enumerable languages for which the complement is not recursively enumerable, and these languages are not recursive. A language L is recursive if and only if this language is accepted by a Turing machine that reaches a halting state for every input word. So that means we start the Turing machine on an input word, and this Turing machine will reach eventually a halting state for every possible input. So in other words, a language is recursive if membership in the language can be decided. We give the input word to a Turing machine, and the Turing machine will tell us yes or no whether the word is in the language or not. The Turing machine never runs forever. So now we are going to prove the theorem on the last slide, stating that the class of recursive languages is precisely the class of languages accepted by Turing machines that reach a halting state for every input word. We start with the direction from right to left, so we are now given a Turing machine M that reaches a halting state for every input word. And this Turing machine M accepts the language L. Now, how do we construct a Turing machine for the complement of L? The idea is very simple. We simply run our Turing machine M. We know that M always reaches a halting state, so M always answers yes or no, and then we simply invert this answer. So if M answers yes, we answer no. If M answers no, we answer yes. And we have a Turing machine for the complement. Now formally, this amounts to a transformation of our Turing machine. We add a fresh state QF, and whenever we have a halting configuration for a state that is not final, so a non-accepting halting configuration, then we add the fresh transition to our fresh final state. Afterwards, we define that QF is the only final state of the machine. So by making QF the only final state of our machine, all the old final states are now rejecting. So the Turing machine will answer no whenever M has answered yes. And since we have defined transitions to our new state QF for all the old halting states that were non-accepting, our new machine will now answer yes whenever M has answered no. So as a consequence, the language of our new machine that we've constructed is the complement of the language of the machine M. Again, this works only because we know that M will halt on every input word. So M always answers yes or no. Now the other direction works as follows. We now are given that L and the complement of L are recursively enumerable. So we have Turing machines M1 and M2 accepting L and the complement of L. Now these Turing machines M1 and M2 do not necessarily halt on every input word. They can compute forever. But we want to construct a Turing machine for the language L that halts on every input word. Now how do we do this? The idea is that we run M1 and M2 in parallel. And here in parallel means again that we alternate between steps of M1 and M2. Now if M1 accepts, then our new machine accepts as well. If M2 accepts, then our new machine stops, but it stops in a non-accepting state. And one of these cases will always be reached eventually. Because our machine M1 accepts all the words in L, our machine M2 accepts all the words that are not in L. So for every input word, either M1 or M2 will eventually accept. And this means our machine M will eventually stop, reach a halting state. And this is a accepting halting state if M1 accepts. It's a rejecting halting state if M2 accepts. So the language of our new machine M is the language of M1, this is L, and our machine M terminates eventually for every input word. The class of recursive languages is closed under complement, union, intersection, difference, cleaning star, and concatenation. Let's prove that this is indeed the case. So we assume that L, L1 and L2 are recursive. By definition, this means that L, L1, L2 and their complements are all recursively enumerable. Now for the complement of L, by assumption we know the complement is recursively enumerable. The complement of the complement is just L, which is also recursively enumerable. So that means that the complement of L is recursive. The union of L1 and L2. For the union we know that the union preserves recursively enumerable languages. So that means that the union of L1 and L2 is recursively enumerable again. For the complement of the union, so the complement does not necessarily preserve recursively enumerable languages. However, in this case, we can argue that it is recursively enumerable again as follows. We can write the complement of the union as the intersection of the complements. So this is the same as saying that we take the intersection of the complement of L1 and the complement of L2. By assumption, the complement of L1 is recursively enumerable, likewise the complement of L2, and we know that recursively enumerable languages are preserved by intersection. So that means that this language, the intersection of these two complements, is recursively enumerable, so the complement of the union is recursively enumerable. As a consequence, the union of L1 and L2 is recursive. And just the same reasoning applies to the intersection. So if we take the intersection of L1 and L2, we know that the intersection preserves recursively enumerable languages. So the intersection is recursively enumerable. Now let's look at the complement. The complement of the intersection is the union of the complements of L1 and L2. These are recursively enumerable by assumption, and we know that the union preserves recursively enumerable languages. So therefore, the complement of the intersection is again recursively enumerable in this case. Hence, the intersection of L1 and L2 is recursive. Now, if we take the difference L1 minus L2, then we can write it as follows. We can write it as L1 intersected with the complement of L2. Now, we know that the complement preserves recursive languages. We've just shown that. And we know that the intersection preserves recursive languages. So that means that this language is recursive again. For the concatenation of L1 and L2, as well as the Kleene star L star, we can basically use the same proofs as we have employed for the recursively enumerable languages. If you recall how we have proven that, we have basically split the input words in parts. For the concatenation, we've split every word in two parts, the prefix and the suffix. And then we have run the Turing machines corresponding to L1 and L2 in parallel to see whether these parts are accepted. And we have run these Turing machines for all possible splits in parallel. Now, if we have Turing machines that always reach a halting state, then this construction that we've done also will always finish the computation. So the constructed Turing machine that we've used for the concatenation and the Kleene star will always terminate if our Turing machines that we've started from terminate for every input word. So we have, for the concatenation as well as the Kleene star, a Turing machine that terminates for every input word. So that means that these languages are recursive again.